Okay, so we'll take our quick look at the calendar. We just spent the last 2 days talking about the chain rule. The fact that it got 2 days of our attention gives you a sense of how important it is. And I think I mentioned it is the most important derivative rule out there, not just of the ones that we've learned already, but of the ones that we have yet to learn. Its chain rule is still number 1. So today we jump all the way back to chapter 1 and we will review exponential functions. So hopefully this will be kind of a day where you can see stuff that you've seen before and not be hit with new calculus things, so kind of a catch your breath day. Next class coming up, we'll do derivatives of the exponential functions that we're talking about today, and then we'll head into some trigonometry stuff. Questions on the calendar? Okay. Oh, one note, next class is scheduled for Wednesday. This coming Monday, there are no day classes because of Columbus Day, right? Okay, so we're starting on page 13. And we'll get a daily summary reader who's ready on page 13. Isaac. Thank you. Ryan, number 1.
Suppose an air freshener starts with 30 grams of gas. 34 grams of air freshener for 2 days after air freshener.
Yeah. Okay, so we've got this air freshener that starts with 30 grams of some unnamed chemical. Let's start with part A here. Suppose that the chemical decreases by 2 grams a day. It's put out into the air by 2 grams every day. So we want a formula Q for how much stuff is left after T days. So anybody come up with this formula?
30 minus 2D.
30 minus 2T, is that fair? We start with 30, and then we lose 2 every day. Great, that's a linear function. Let's come over here to part B, which says we're losing 12% a day. It's definitely not going to be linear, because linear would assume you lose the same amount every day. Okay, so we're going to start with exactly what we started with before. How much is that? 30. Levi, you have an answer for this one?
30 times.
Levi says times 0.88 to the T. Levi, where did the 0.88 come from?
It's 88% because you're losing 12% a day. So and T is each day. So every day that you go, you multiply by that.
Yeah, exponential functions, of which this is an example, are good at telling you what you have, not what you lost. So how much do you have left over? Well, if you lose 12%, you still have 88%. And so what we can do is take this 30, and the next day we multiply it by 88%, and the next day we multiply that new answer by 88%, and we just keep multiplying by 88%, which Levi has correctly captured here with the 0.88 to the T, all right? And we'll put a little dot there for times. Okay, so number 2, we'll go to Brendan. P sub 0. Mm-hmm.
Note that we insist that A is greater than 0. A is greater than 1. We have an exponential.
Okay, so let's pause right here. So I've labeled a couple of the numbers we had in our air freshener example. The 30 is the P sub 0, the initial population of this chemical. And then the base is this 0.88. That's taking the role of A in this kind of generic exponential version. Let's skip this sentence that Brendan just read and go to the next one. If A is between 0 and 1, which it is in this case, it's a 0.88, then what kind of exponential thing do we have? That's an exponential decay, which makes sense because we're losing air freshener every day. But if that base were bigger than 1, then we would call it exponential growth. Okay. Yeah, so that's why we say don't make it equal, don't let it equal 1. So we're going to come back to number 3 in just a minute, but I wanted to pull up an article that I was reading yesterday. So probably you've heard about the Ebola virus in the news recently. And I found this article. This is in the Washington Post. There were a couple of things that I wanted to point out. So first of all, can we read this in the back? Okay, so the first thing I wanted to mention is this right here. Says the number of Ebola cases in West Africa has been doubling about every 3 weeks. What kind of a function doubles every period of time? What is it? It's an exponential growth function because we are multiplying by the same number over and over again. The other number that we need, so this doubling business is going to be part of a formula we're about to write down. But what's the other number we need if we're going to write something like this? Yeah, the 3 weeks will definitely come into play. We need the initial amount of stuff. Okay, so the initial amount of stuff is down here. It says as of Wednesday, the WHO released this number. This is the most up-to-date number that existed when this article was written. 8,033 cases, and then this is how many people sadly died out of those 833. So let's see if we can write down a formula modeling this scary Ebola outbreak. So we'll call it P equals. So still starts with the initial population, which we saw was 8,033. And then we're going to multiply by some number to the T. All right, so the sum number, anybody know what it is? It said doubles every 3 weeks. What's the magic number? A. It's 2. Because to say you're doubling means you multiply by 2, and then you're going to multiply by another 2. And if you keep repeatedly multiplying by 2, that's 2 to some power. So it's going to be 2 to some power, but it isn't quite that. In fact, why don't I, let's use W for the number of weeks. It says it doubles every 3 weeks. That formula would say it doubles every week, even scarier. So how do I make it so it doubles every 3 weeks? Yeah, we're gonna take that W and cut it into thirds. So every 3 weeks, that power bumps up by 1. Levi.
Is that equation accurate if you're calculating somewhere in between the 3-week section?
It is actually, yeah. So this formula agrees with what we expect if the W is a perfectly nice multiple of 3 weeks, but it also gives you an accurate picture of what's happening after 1 week and 2 weeks and everything in between. Okay, so that's the formula. So for example, if I wanted to figure out if this trend continued, doubling every 3 weeks, I wanted to know how many people might be infected come the end of this school year, the end of this calendar year. What would we need to do first? Yeah, how many weeks until the end of this calendar year, right? That's what we need to know. Okay, we can figure that out. So let's start with the week coming up. So I have 1, 2, 3 weeks there left in October. Let's say that November and December have like 4 or 5 weeks, so maybe 9 altogether. I'm not looking at it, but roughly 9, plus these 3 gives me 12 weeks. So what are we doing to our formula over there? Plug in 12 for W. So 12 goes up there for W. Maybe we can use our function notation. P of 12, 8,033 times 2 to the 12 thirds. So this one we can at least do the small calculation. So 12 thirds is 4, 2 to the 4 is 16. Somebody have a number for me here? That seems too big. Wait, no, it seems reasonable actually. Is that all right? Okay, and then let's suppose that that the outbreak continues following that pattern, and let's take it to a year from now, right? 1 year from right now. What would we do? Yeah, 1 year from today. P of 52 is what we're after. So it's 8,033 times 2 to the 52 weeks in a year, right? Approximately. All right, 2 to the 52 over 3, and then times 8,033. Who's got it for us? Go ahead, just read them.
1, 3, 2, 6, 5, 7, 2, 6, 0, 7.
Comma, comma, comma. How many people are in the world right now? Aren't we around 7 billion right now? I think we're at about 7 billion. So what is this number?
A lot.
Yeah. It's over 1/7 of the population, and if it continues, I mean, we will exceed the Earth's population just a few more weeks from here, right? Like imagine doubling this number just a couple more times, and it will get higher than the 7 billion that we're at. So, so last thing I want to say about this is one other quote in the article. Let's see if we can find this up here. There we go. So according to whoever said this, let's see, Tom Frieden, director of the US CDC, people don't understand the concept of exponential growth. And you guys are looking at numbers that like our mind just cannot comprehend doubling for very long. We just aren't programmed. It's not a matter of like we should work harder or be smarter. Our brains are not hardwired to understand this kind of growth. Okay, let's see. So let's come back here. Kind of hard to follow that by jumping back into the packet. Yeah, Levi.
Could you email that link?
I will email the link. Okay, so let's come on back to number 3. And I think we're up to Kyle.
Instead of writing P equals P sub 0 A to P, we choose the base A, we could instead use P equals P sub 0. This equation is used for growth.
Okay, so we've got basically 2 exponential formulas. The first one is this P of t is P0 A to the t. The other one is this version, which has the number e in it, which you'll remember is like 2.7 and change. And so the way that you know that you're using this thing with e is that you see the word continuous. When you see continuous, you use the e formula. If you don't see the word continuous, you're probably not using the e formula. Sometimes you have a choice. But all I can say definitively is if the word continuous is there, you better be using that e formula. Okay, so if the value of k, which is right up here next to the t in the exponent, if k is positive now, then it's exponential growth. And if k is negative, then it's exponential decay. And we'll go back to Kyle. E is?
E is an irrational number approximately equal to except 20. Its
Derivation.
derivation can be found in
Okay, so let's go to Cameron for 4.
What is the continuous decay rate that corresponds to 12% decay rate?
Okay, so let's take a look at 1b. So what we had before was this equation, was 30 times, what was it, 0.88 to the t? That's what we had. But we want to rewrite it because what keyword is in this sentence? It's continuous. And so if we're saying continuous, then we better be saying the formula that we just saw, P0e to the kt. See it? So all we're doing is taking the formula we had and we're thinking about it in this new e way. Okay, how much is the P0? It's 30, so I'm just going to make a note of that and then I'm going to ignore it because they're both 30 and we can just ignore them and get to what we're after, which is the k. So that means our equation is now 0.88 to the t equals e to the kt. And what we're after here is this continuous decay rate. What letter do you think represents the decay rate in this new equation? One of those letters is the continuous decay rate. It's the k. The t is time. That's passing regardless. E is just a number, even though it's a letter. It's a number. It's the k that we mean when we say continuous decay rate. So maybe I can circle that there. So continuous decay rate is this k right here. Now at the moment our variable k is up there in the exponent. So what do we do to get a variable out of the exponent? It's logs. Now we have a day coming up where we'll really review logs, so this is like kind of jumping the gun just a little bit, but I think you've seen it before. So what we're going to do is hit both sides with a natural log, ln. And one of the nice properties about logs is that when you see log of something to a power, what can you do with that power? You can bring it right to the front, yeah? So we're going to take both powers and put them right in the front of the logs. So this becomes t ln of 0.88 equals kt ln of e. And then there's going to be a lot of action happening in a short period of time right here. What cancels on both sides? T's cancel. Just divide both sides by t, which is good because t wasn't what we were after. We wanted k. And then ln of e is 1. Again, we'll see this soon enough. But you might remember that ln of e is just 1. So that means that k is ln of 0.88, which you can type on the calculator and get a decimal. Isaac? Okay, about negative 0.128, which as a percentage is about negative 12.8%. This is close to the 12% that we saw before, but this is kind of the continuous rate as opposed to like a daily rate, which that 12% was. Brendan?
Is the K supposed to be?
In the equation, the K has to be written as a decimal, not as a percent. I'm changing it so we can compare it to the 12% we saw up above. Okay, and then finally, before the activity is number 5 here. Let's go to Levi.
Let's sketch a generic exponential growth curve. Generic exponential
Okay, so we're just going to draw generic exponential growth. So exponential growth, is it going to start high or low or in the middle? High, low, or somewhere in between? So like low down here? 0, right? Got to stay positive, but it can get very close to 0. So there, and then growing as we go from left to right. And we'll just put a little dot right here. And we know the coordinates of that point. So what is that point there? Normally it would be 1, because we know that any number to the 0 is 1. So this piece right here becomes a to the 0, which is just 1. So the whole thing, though, becomes piece of 0 times the 1. So it's piece of 0, which makes sense. It's our initial population. This is basically when we start the clock. And at that moment, we're just calling piece of 0 the initial population. Same kind of thing for a decay curve, but here we start very high and then we decay, getting close to, but technically never equal to 0. Okay, so the activity begins on the next page. Depending on how quickly you can get through that, you might have some time towards the end of class to start or continue working on one of the projects. So let's see how far we can get.